name is Patric Wanko, and this is what I will be presenting about assessing the applicability of schooling genetic algorithms to product design. I already made a talk in the past in NCAT, and it was about schooling genetic algorithm, and now I will be talking about the connection between that and product design, and also where I am right now in the future direction. This is the agenda. So I will start with a review of schooling genetic algorithm. If you remember, schooling genetic algorithm is an adaptive meta-heuristics, and it is derived from genetic algorithm. To people who are used to population research, by the way, is my background, they will have a fair idea what it is about. And it is biologically inspired by fish schooling. So it is GA-based, and it is a model that enables process and operator adaptability. How does it do it? It does it by mimicking fish schooling. So within schooling genetic algorithm, the traditional crossover, mutation, and selection operators of genetic algorithm, they do behave differently depending on the select operations of fish schooling that I decided to implement within this algorithm. A little bit of terminology for some of the terms that I will be using. An SGA fish is a candidate solution to a problem. A local cluster of fish is what I refer to as a school of fish. And fish, they have discrete membership to school, and it is driven by member proximity. And the definition of food or predator, it is relative. Here I have an example. This is in the case of, let's say, a maximization problem, where I'm trying to find the best solution to a maximization problem. In such a problem, food will be anything that drives my search to what I want. In this case, a higher value of my objective function. And the predator will be anything that will drive it away. So the abstraction from fish schooling that I'm actually implementing in SGA are the food foraging, predator avoidance, and the school maintenance / the merge. How are those abstractions working? For the selection of regeneration, I actually have developed a non-parametric clustering algorithm, which at the beginning of the algorithm, at the very beginning, once I have the initial random candidate solution, will just go in my search space and cluster and create a cluster based on the proximity. So I do not tell my algorithm the number of initial clusters that I want to have. The algorithm goes ahead and figures it on its own, depending on the density and how close the solutions are from one another. In food foraging, this is the behavior that occurs when CF here is the center of the current average fitness. The fitness here is each school has a center of mass. You can think of that as the center of mass from the body, which is that very central point from all the mass that it contains. So here the center of mass of the school is that unique point that I use to derive all the different behavior that the school is allowed to be, to have. It can be food foraging, predator avoidance, or maintenance. So this one will occur when that center of that when the current average fitness is out of control, meaning that it is high. So in my maximization problem, it means that my solutions are actually going towards an area of the search domain that I want, something that is going higher. Predator avoidance is happening when my current average fitness is low relative to the present average fitness. And it is happening, when it happens, it means those solutions that are part of my cluster are actually close to an area that I do not want them to be. So what happens is, in such a case, the mutation operator is going to be predominant. And the way it works is I start the mutation followed by crossover. Here on the screen, those black dots words that you see here are, let's say, some solutions that I have. It will show you how parallel avoidance works. So here I have some solution here, and then the green dot represents that center of mass, the center of my school. After assessing this value, I realize that this center of mass the thickness is low compared to what I actually know. So what do? I start with mutation. Using that, I start generating some muted solution in a direction further away from the school. Once I have that mutated solution, I now use them as the parent for the crossover. This is to mimic the fact that when a school a fish is flying, is swimming away, the fish from the periphery are the one that get away first, and the rest of the school will follow. So once I have them, I choose them, and then by mutation, I will have some solution that will be generated somewhere in between, ideally. This is an overall view of the schooling genetic algorithm research mechanism. This is a snapshot at different generations. So at generation N, I have this school here, 1, 2, 3, and I also have this other school here at generation N. So assuming that the storage processes guide this school from here all the way to this one at generation N plus, I want to say 4. And that the same storage process drive this cluster of fish from this point all the way to here. As soon as the cluster reaches this point, the storage process will prevent the cluster from going here to this location. Why? Because this school of fish was already here some generations away. And because it was here, what I did was to log a value that represents this area in something similar to a table list. And what happens is this cluster is forced to go search another area of my domain. It is no longer allowed. And no other cluster will be allowed here for a certain time. And this behavior here is mimicking the depletion of food, which is happening, that happen when fish feed from place to place as they move. This is very high level, the life cycle of schooling genetic algorithm, how it works, and those are the main parts that I said earlier. Depending on the status of the school, the crossover rate or the mutation rate will be more predominant, will be higher than the other one. They will not just be applied on a systematic way. So now we will talk about product design before making new connections. So how did I get there? First, we started from this change in nature of the product. Here I have the example of a car. Cars today are not what they used to be. Today they are computerized. And this have made product behave more like biological being in that sense that today a car can sense the environment, it can act on the environment, a car can think while the driver is there to actually help the driver, assist the driver. So industrial and automobile is more like a biological being. How did we get there? One of the methodology that have enabled that is IPPD, which stands for Integrated Process and Product and Process Design. I looked at, mainly we have the waterfall model, the V model. I just looked at the IPPD because I saw that it captures the essence of what I want you to look at. Here in the IPPD, in the design process, we have the consumer. Usually, we are the input provider to the system. What we provide to the system, and on the other side, we have the engineers who are the sole expert of the system. What the consumer provides, they are using axiomatically, the engineer turn them into requirements. After we turn that into requirements, we go ahead and we propose a design or prototype for manufacturing. And this prototype is usually a very optimized version is the best prototype that the engineers were able to come with. But the problem is this methodology, which is still prevalent today among others, does not really take advantage of the fact that today objects such as a car have that capability, are smart, and they have those high-tech tools, they have that capability of thinking on their own. And this one brings us to the current limitation of product design. So the limitations are that traditional product design, they do not give the product designer the holistic view of the life cycle performance of their product. The product designers sit there, they look at what the customer wants, and then they turn that into a prototype, and then they send it to the factory. The traditional product design approach emphasizes three main things. One is the design optimization into a fixed configuration. That comes from the prototype, which is usually the best that the engineer could come with. They send it for mass production. System decomposition to facilitate system analysis. The consumer, the user, they come, they say, this is what we want in the product, and then the engineer will run from that to determine the functions that they want in the product to find out if those functions will actually be required. And so they have to decompose in order to well understand what we get into the product. And this is a way we are trained in the engineering. When we have a big problem, if you want to solve it, we decompose it to have a break. We break it in pieces and then we tackle each pieces independently. And the third thing is the central role of systems engineer for design and sustainment. The engineer is the expert. When something goes wrong, we call the engineer. And when something goes wrong, we call the engineers. And this is really not good for sustainment. So how do we address that with fish schooling? We go into the life cycle engineering context. I have said earlier, my research topic is about using life cycle data for sustainable product design. And the data in the life cycle is potentially huge. And the data is definitely heterogeneous. The optimal solution for a problem is not known. But using some approach, there is a way to test the solution to find out whether it is better than the previous one. So, still in the context of the research, here are some definitions that I have. The first, sustainable product, in my case, is sustainable product design. It should yield a product that is modular, that is interoperable, that has some level of configurability and flexibility. And I refer to this as the evolvability feature. Sustainable product design, it should yield a product that is differentiable and have some system efficiency due to the economy of scale. It will cost me a lot of money if I have many different products and each product has a unique configuration, because then I need to find out which configuration is the best for each product, and that is not good for me. Meanwhile, if I have a configuration that can be common to some of my products, it will help me, and this is where the economy of scales gets into place. And I call this the grouping feature. And finally, sustainable product, well, it should be sustainable. And here I mean by that, a product being able to operate with minimal intervention from the user. This is the sustainability feature. And with this, then, I was able to define the actual problem that allowed me to connect product design with schooling engineering algorithm, which is what analytical tool can be used that can allow the incorporation of those features, innovability, grouping, and sustainability into a characteristic of a product. And in order to do that, I had to define a life cycle-based product design process. So how did we do that? How did we get there? Here is one typical example, the Sequence KS-70. It is a helicopter, it's a product that's being used by the military. The Army uses it and calls it the Black Hawk. The Coast Guard uses it and calls it the Jayhawk, and the Navy uses it and calls it the Seahawk. Different models, different missions, they operate in different environments. Just the maintenance of these helicopters costs the DoD on a yearly basis hundreds of millions of dollars. Meanwhile, it is the same model, and across the different, whether it's Army, Coast Guard, or Navy, they have a lot of components in common. But because it is being looked at as if it is a separate product that each military uses, it ends up costing a lot of money in terms of inventory and in terms of maintenance. But by considering those three attributes, it can be brought down significantly. A way to look at that, looking at the Sequence scheme, will be considering a product which is being impacted by three types of parameters. This is a characterization that came up with that any life cycle data can be categorized, can be put into one of these three categories: environmental parameter, operational parameters, and design parameters. And this is what is impacting the performance of the product. But what are those actual parameters? Here I have a definition for each of them. The design parameters, those are the ones that are being manipulated by the engineers and the factories. They are qualitative, they are quantitative, as well as the physical and functional characteristics of the company. And some example, we have the layout of the product, the material that is being used. Are you going to use aluminum? Are you going to use steel? Are you going to use hard plastic? The sensors, what type of sensors, or the functions, what type of functions are you going to include? Those are the design parameters. We have the operational parameters. Those are functional attributes that can either change such that the value can be set by the use of that product, or whose value can be quantified in terms of count because of its use by the consumer. What do we have there? We can have the type of use, we have the frequency of use, we have the number of resets, and finally the environmental parameter, the last category I mentioned earlier. These are the attributes of the context or environment of the products being operated or used. So we are part of the process around it. These are the ones that we really have a little bit of control or no control at all. And those will be temperature, let's say the location where it's being used, or the infrastructure. Another way to look at all those three parameters is to look at the life cycle. The design, the value is set by the engineers. Once it is set, it is done. We cannot change it. If it has a serious impact on the performance, then the user is the one who is going to suffer the consequences while using it, because they will have to adapt to the product instead of the product adapting to the user. And the evolution cycle is low. Which stage of the life cycle engineering is it being set? At the beginning of life, the BON. The operational, those are set by the user. Evolution cycle, very fast. Right now, I can take my phone, I can decide to use it to make a call. In a minute, I can decide to use it to play music. I just change the mood. So that is an operational parameter. And when is it being set? During the beginning of life and the end of life. And finally, the environmental, the one over which we have, the value cannot be set ideally in the evolution cycle, no evolution cycle or life cycle engineering stage. So how do we combine all those product design and school genetic algorithm? Just going to the gist, this is how we get together, where we have the design parameter, the operational parameter, and the environmental parameter that get into the design product. Once they get into the design product, we currently, the method that we currently have, we will be focused on this one here. Now, what is being suggested here is to look at the entire life cycle and to consider this. One of the possible advantages when looking at such a thing is when it comes to the prototyping of a new product, we can use existing data from the life cycle to have a rapid prototyping. And with the prototyping that we will know will be less than likely to change because it will already integrate from the very beginning all the data that was collected during the life of similar products. So the experiment that I made, I made a couple of experiments, and the one that I want to share with you was the experiment that I made using just a hypothetical product. So this one was not an actual product that I had, and from the product that I had one environmental parameter that was discrete, and I had one design parameter and one operational parameter. They were both continuous. The performance in one experiment, it was a function of the design parameter only, and in the other one, it was a function of the design and the operational parameters, depending on the environment. The stopping criteria for the simulation was I had to, one was the maximum number of generations reached, or if I have no variation in the overall population fitness for 3 consecutive generations, the simulation was to stop. I used MATLAB to run the simulation. The metrics was the number of generations to converge, the quality of the solution obtained, the best solution, and one of the metric here that I really want you to look at is this one here, the TPI, the Trait Performance Index value for each life cycle engineering parameter type. So this is metrics here is being defined here is similar, if you're familiar with the time-motor distance, which is being used in similarity method, and also with the relative error. You will see that the Trait Performance Index, ideally, it is a metric that we want to use in order to assess whether a parameter should be kept by the designer as a design parameter, or if a parameter that the designer wanted to keep as a design parameter should be changed as an operational parameter, depending on the impact that it has on the performance of the product. So for the first experimentation, where the performance in both environments was in one environment dependent on the operational parameter, and in the other environment it was depending on the operational or the design parameter. These are the results that were obtained. A conversion was obtained at around 60 generations, and the school average fitness was reached 1 towards that 60 generations. So I didn't work all the way to 300 generations because it means the second stopping criteria was actually reached, was actually observed by the simulation. And what is interesting here is the behavior per generation. Here, red represents school maintenance, green represents predator avoidance, and blue represents food foraging. When we look here, we can see that at convergence, the only two behaviors were existing in the population. Those are the predator avoidance and the school maintenance. Food foraging was no longer there. Considering the fact that food foraging was only there when the population was in a good spot and after that was forced to leave. So this one, an interpretation of this is that with the environment that was used, food foraging, the population converged, and the environment was not, because the environment was not changing, those measures to push the population away were actually defeated by the optimization The TPI here were 7.73, almost identically the same, and in the environment it was 2. The maximum value of the TPI is 2. So for the environment, what does this mean? It tells me a high TPI of 2 for the environment. It tells me that the performance was reached in both environments. A TPI value of less than 1, what the figure is telling me is that not all the operational, not the entire spectrum of the operational parameters should actually be considered by the designer. So the designer actually have an opportunity here of fine-tuning the product. The second one, also for the TPI, gave us almost the same value. Here it was slightly higher. What caused this difference? This is something that I am working right now to find out what to have a very clear, concise definition, interpretation of the TPI value. What does it actually mean when it falls within a range? What is the threshold value? At which point can the designer decide, okay, rather than having this functionality on my product as a design parameter, it should be on my product as an operational parameter, because it is being used a lot, and since it is being used a lot, it will make sense to have it as an operational parameter to have the user deal with that. So the future iteration here is to apply the method to the environment with evolving characteristics. The simulation were made on a static environment that was not changing at all. Applying the method to problem with complex design attributes with noise also. Here I only use 3 attributes, say 1 discrete for the environment, 1 continuous for operational, and 1 continuous for design. And the goal is, right now I'm working with 7 parameters. So I'm including more parameters on the design, on the environment, and on the operational side. And also studying the impact of the TPI on the SGA result and its meaning to the designer. This goes back to what I said earlier. What actually does it mean if my TPI is, let's say, less than 0.5? Does it mean that that attribute that represents the size of my product? Does it mean that the size should not be that big that I can reduce the size without impacting the performance of the product? Or does it mean that to have a better performance, I should increase the size of my product? And this is it. Do you have any question?
Can I ask, to what extent do you think you require the features of the schooling genetic algorithm to be able to attack this kind of problem rather than a standard genetic algorithm? What would you expect if you used a normal genetic algorithm?
Okay, so the normal genetic algorithm doesn't have a grouping feature, and also the normal genetic algorithm is known to not perform well on changing environment. But here, since we have that feature that not only will push the search process towards a good solution, but will also push the search process away from a good solution after that solution has been reached. So the traditional genetic algorithm does not have such feature built into, and they usually cause what is known as the premature conversions. Once a best solution is reached, then it will just stay there, and it will force all the other solutions to converge as time will go. But the schooling genetic algorithm does not allow that. So the second one is
you look at it primarily as a way of responding to a dynamic environment then, is that right?
Yes, we are responding to a dynamic environment and also a way of exploiting the characteristics of the environment by using the grouping. I am not that interested into a good solution if that solution is not differentiable. And grouping is what allows me to focus on the solutions that are differentiable.